So today I'll be talking about angularity event shapes in high energy scattering. So this work is done in collaboration with Daqiang Kang at Fudan University, Shanghai. So here is my plan of the talk. So I'll briefly give some introduction on event shapes, angularity. So we have already one talk by Radici Sharma on angularity, and so here I'll be starting with very basic introduction. Then I'll be going to directly DIS angularity, mostly for the beam function calculation. Then I'll show some steps for the cross section at NNLL accuracy. Then I'll make some conclusive statements for which will be useful for EIC. And then I'll be quickly showing some results for our recent work, Q goes to GG. So since we are gathered here for EIC, so I'll be mostly focusing on DIS part. Okay, so quick overview of jets. So after the high energy interactions, a bunch of collimated hadrons comes out. So we used to call, we usually call this jet. And you can see here a nice like picture from Petra, which is the final state configuration of Petra, which is one of the major discovery for gluon discovery. So in between this jet, because of the high virtuality of the pattern, we can have collinear and soft splitting. And finally, it hadronizes at large alpha. So, so our motivation is, like this community motivation is to study this jet configuration. So we usually address this jet physics by addressing the jet observables, which are called jet event shapes. So we have several jet event shapes: thrust, jet broadening, angularity. Thrust is mostly extensive studied, and jet broadening also studied more or less well. Angularity is little bit something we will be focusing here. Okay, so let's start with the thrust. So this is the definition of thrust. Q is the hard scale of the interaction, and P perp is the transverse momentum of the ith particle of the jet, and having rapidity for the ith particle in the exponents, and we sum up over all the particles. So what does this definition gives? Let us understand. For example, in case of electron-positron going to QQ bar and G, so if we consider one of the particle is my thrust axis, then we can redefine this definition for this process by having the projection of the ith particle's momentum towards the thrust direction. And the definition looks like this. So if you consider, like for the time being, like there is no one only QQ bar state, final state, then this projection will give out to be exactly 0. So in other sense, we can think of it, if the calculated thrust measurement, if thrust goes to towards 0, then we can have back-to-back jet configuration. If it goes to 1, then we'll have multi-jet configuration. In some sense, thrust can give you a geometry of the final state interactions. Let's focus on the angularity, which is the essentially we are going to talk about. So angularity will have this kind of modification in the definition, having a very simple continuous parameter A. It looks like very simple, but it does actually a lot of things. Let me go slowly one by one. So if we look at this angularity parameter space, which is pictorially drawn here, so you can see that since this is a continuous parameter, so continuous parameter, by regulating this continuous parameter, we can actually access all the other global thrust in a single angularity study. For example, if A goes to 0, that is basically exactly the thrust limit. And if it goes to 1, it is the jet broadening. Another event shapes, I will not be talking about this. So in some sense, this study of angularity includes many more other previously studied event shapes. So in some sense, it is a more general like study of the event shapes for a process. For example, electron-positron going to diazide. So in this case, so now this projection is having the functional dependency of the angularity parameter. Changing this angularity parameter, we can have a different configuration. Okay, so far this is the status of angularity study. So this upper level is for the experiments, lower level is the skate results. So if we look at the experimental approach for thrust, like pretty much we have studied DIS in HERA and E plus E minus in LEP, and also like LEP has some results, some remarks on the angularity also. But we have not come up with the DIS angularity result yet, and EIC could be the best place for that. And if I look at the soft collinear effective field theory approach, so thrust is extensively studied by these guys like Jan Stewart, Baker, and so on. And again, we have few more for the PP also by this group. And DIS for thrust is also addressed by this Chris Lee and Dai Qiang at UCSD, I think, University of San Diego. So broadening is also more or less studied. But in case of the angularity, E plus E minus angularity is studied by like Lee and Bell and these groups, and also this Felix has presented, like reported this angularity for the photo production. So our plan was to address DIS angularity for this range. So we published this work, so I'm mostly going to talk about this work. So why DIS? One of the aim you can think of, the most precise thrust and C parameter findings is sitting here, which is having a 3 sigma discrepancy from the lattice result. So we need to have new machine, and we better try some new observable rather than thrust and all. And since EIC is also has included in his yellow paper the global thrust measurement or event shapes measurements, so in some sense our prediction could be one of the early milestone for future EIC in this direction. So let's start with the angularity for particularly deep inelastic scattering. So you all know that deep inelastic scattering is hadron and proton and electron is scattered, and then a bunch of hadrons are coming out. And in this case, if we like compare with electron-positron going to diazide to electron-positron going to electron-proton going to diazide, then we can see that in the diazide configuration, we'll have one final state radiation and one initial state radiation because of high virtuality of the high momentum of the proton or partons inside it. So in principle, like we don't have that freedom now for the back-to-back channels like we had for the electron-positron to diazides. So in this case, we redefine the unit vectors in terms of the beam direction and in terms of the jet direction. Then we redefine the angularity definition in terms of the projection towards the beam and jet part, and which is also having this functional dependency of angularity parameter. So our final aim is to calculate the cross section, angularity differential cross section. So we have this hadronic tensor, and by using like factorization in skate, so we can write down this angularity cross section in terms of the hard part, beam part, which is coming from the initial state radiation, and the jet part, which is this one, and the soft part of all. So let's look at little bit more in the factorization and power counting. So power counting in SCATE, actually the moment, the collinear momentum and soft momentum power countings are different. You can think of like lambda is a like scale parameter. So eventually when we relate the scale parameter, it comes down to be like a dependency among the collinear and soft. And eventually we get this collinear and soft momentum dependency like this. Now if we draw in the p plus p minus phase space, then we can see that the collinear and soft part is clearly factorized. And in this way, we factorize the beam and jet functions. So in this DIS case, one should think of that our beam is also one of the collinear part. Okay. Okay. So now what is the status of the different distributions? So the jet function and soft functions are basically studied by these guys already. So here in this work, we focused on the beam part, which includes the which is coming from the initial state radiation. So beam part is can be written as a convolution of the non-perturbative part and the perturbative part, which has like NLO term coefficients and NNLO coefficients and so on. So particularly in this work, we focused on the NLO. Okay. So NLO has this kind of configuration. We have double logs, single logs, and one single log couples with the splitting function. Okay. And we have this guy sitting here like constant term. So we mainly focused on this constant term, how to calculate this constant term at one loop beam function. So the way is we go to the standard way is we go to from tau space to the new space using Laplace transformation. Then we do the resummation and all the calculation. Then we will come back to again the tau space. Okay. So a little bit of resummation here. So at the initial level, we have three different most scales. One is the hard scale, one is the jet or beam collinear scales, and another one is the soft scales, which has the A dependency. Now we design the profile function such a way that during the evolution, resummation, we go to the particular hard scale. Okay? And the standard practice is doing by RG, and here is the kernel who actually gives us the order by order resummation of the large logs. So here we will be addressing up to next to next leading logarithm in an LL. Okay. So one just pictorial understanding for the resummation. So this is the data for E plus E minus. So order by order, like alpha order perturbation series inclusion also gives you like divergence in the low tau region. Okay, so when you include this resummation of large logs, so essentially it converges to like 0, and you have the satisfactory result you wanted, which satisfies the experimental findings. Okay. So let me show you now resummed result for beam function and the differential cross section. Here is the result up to NLO, and as I said that this beam function also has dependency over this angularity parameter A. So this is the thrust result for the beam function at NLO. And this is like A goes to minus 0.5, it is for plus 0.5. And if you look at the color coding, so this gray is basically NLO result without resummation, then green to red is the order by order resummation, and you can see that the resum result actually gives us the more precision, significant precision. And surprisingly, we noticed that we got very significant precision in the negative A region. Okay. Now, the angularity differential cross section. So we started with this factorization, then we did the resummation, and the resummed total cross section looks like this. Let me just briefly tell you the sections of the equation. So this red two parts are basically the collinear beam functions here. And this part is the jet function, which has this large log dependencies over here. And this is the soft part, okay? Now, if you, this line actually are the factors coming out after the resummation from the anomalous dimensions, okay? So these are basically the part which actually gives us the convergence of the large logs. Okay, so now we use this expression to perform the numerical study, and we come up with the numerical result for the cross section up to next to next leading node. See, here is the result. So this is like tau axis, and this is the differential cross section multiplied by tau. So as usual, our NLO result shows divergence in the low tau region, and the resummation actually gives us convergence. But if we go order by order higher resummation, we get very more precise uncertainty band. So we are mostly interested for this tail region, and this is a equal to 0 result I'm showing here. But for a non equal to 0, I'll be showing later. So we are mostly interested in this region for the EIC kinematics. And if you look at the relative uncertainty here, so that shows that we have pretty much like precision we got up to an NLL. And we did not consider the higher part of the tau because that might include the like higher like full KCD calculation we may need. So we are mostly interested in this region, this tail region. Okay, so now the angularity parameter study. So as this cross section also depends on the angularity parameter, so you can think of angularity parameter is kind of a part of the kinematics now along with the x. So this angularity parameter has this kind of dependency. This is for negative A, this is for positive A. And we again for the cross section we have seen that for negative region of A, we got the more precision. And here is the relative uncertainty plots, and red line is the negative A regions. So the bottom line of this finding is basically to have more precise result, we should concentrate on negative A region. But how negative we can approach? So it actually gives the boundary from the SCAT1 factorization. So if you go approach like A equal to -2, then soft and collinear will be exactly like very close, so it will be very difficult to use SCAT1 factorization. So I think the descent order of A would be like -0.5 or -1 maximum. Okay. So now X dependency, we have also seen that X approaches to the smaller region, the uncertainty is smaller. And our reporting from this study is our result is more precise for negative A and X approach to small. So another byproduct we got from this study. So at NLO, the beam function which is produced from the initial state radiation, and without calculating fragmentation function explicitly at NLO, we can directly have mapping through the crossing symmetry in the space from here to here, because if you see this diagram, it's on cell going to the off cell, this is the off cell going to the on cell, so we have the crossing symmetry in the phase space. So using that, what we have seen that only in the NLO cofactor of the beam function, we have only a sign change of the log term, log x term. And interestingly, the coefficient of this term is A dependent again. So the difference between these two can be regulated by the value of A also. Okay, so so far I discussed about the DIS angularity. So let me just quickly go through the recent findings in this direction for Higgs to glue at NNLL accuracy. So we all know that Higgs decay channel has contribution from several channels, and here is the pie diagram of it. And the current accuracy is Higgs for angularity measurement for Higgs going to QQ is NNLL prime, and Higgs for glue is N2LL. So our goal was to address NNLL prime Higgs to glue. So what is the difference in this? The difference is basically, you can see this plot. So all the anomalous dimensions and beta functions will remain the same order, but the distributions functions we need to calculate at 2 loop. Okay, so we calculated, okay, so this is the decay rate for the Higgs. So we have the bond part, then this is the top loop configuration. This is basically the hard configuration, and we have the collinear parts and then the soft part. So all these three are actually given very a higher order calculation. Some of them are 3 loop calculations are done. So, and in case of the collinear and soft part, so angularity soft functions is calculated up to 2 loop already by these guys, and jet functions for quark, it's 2 loop, and gluon for 1 loop. So our aim was to calculate the angularity jet function for 2 loop. Okay. So here is the result. So again, I showed the result for A dependence result because the angularity parameter is crucial here. So if we see again the trend of the resummed precisions, so what we found that again the negative A region is going to give us more precision, and we found that from going from N2LL to N2LL prime, the uncertainty for the lower A is having the 12% corrections, and uncertainty for positive A around 0.5 is having 5% corrections. Okay, summary. So so far we addressed DIS angularity, and we have calculated up to next to next leading logarithm accuracy for cross section, and as well as the beam function, 1 loop beam function. And we reported that the negative A and small x region could be the good region to study in terms of the output of the soft collinear effective field theory. And this work could be one of the early milestones for EIC measurements. And I have also showed our recent work on this direction for the Higgs to glue. Okay, thank you.
Thank you. Is there any physical understanding why these uncertainties are small for negative A?
Yeah. Actually, we are trying to understand that. So I think Rishi Sharma also showed the result same, like for negative A and all. So I also talked to him regarding this. So our present understanding, I'm not sure whether it is absolutely 100% correct or not. Our present understanding is it may come from the scale dependency. So now our scale is having dependent on A, because as I showed the collinear scale is having the power of 1 over A1 minus A. So whenever we are changing A, so scale itself is changing in the evaluation. So that is one logic we thought actually. Yeah.
Okay, thank you.
Any other questions?
Probably you can also.
I missed that part where you computed the fragmentation functions. There was a pole at A equal to 2. There were so like if you do a full resummed calculation, do you see this pole going away? Like after when you're computing any observable?
Okay, so actually if you look at this picture, I already shaded some region of a parameter. I did not very much discussed about it. Since you asked, if you look at this region, I did not include a equal to 1. The reason is, if you include a equal to 1, then your exponential lecture vanish. Your definition is fully dominated by the transfer structure. Now, state 1 factorization is no longer valid there.
So here,
Yeah.
you didn't include a equal to 1, but let's say a equal to 2 is a valid choice.
Okay.
And in one of the fragmentation function formula you showed, there was a factor of 1 over a minus 2. So that should give you some sort of singularity in your calculation.
No, that result is the manifestation of state 1 calculation, and state 1 is not valid for a equal to 2. That's what I'm saying. We cannot go beyond 1 even, around 1 even. So we need to have another factorization technique. Maybe that functional dependency will come out to be different.
Okay, that will regularize that.
Right. But I'm not sure how it will work, but yeah, might.
Just a quick question about the hadronization correction. I don't know if you included that, because there's like a global event shape, right? Is there a similar shape function where you expect some universality to other processes, or would that now depend on sort of multiple directions that would make it more complicated?
To calculate the fragmentation part, you're saying?
No, like if you account for a hadronization correction, right? If you were to include some kind of shape function or so.
No, we did not use any shape function at all in this calculation.
Okay, but do you know if that exists, or if there's some way of accounting for that? Because it's relatively low energies, right? So you might worry about that.
Yeah, maybe right now I cannot, I cannot answer this. Probably I can. We never thought in this, right?
No.
Yeah.
Let's thank the speaker again.